these bugs tend to hang on a little bit too. So please wash your hands frequently. If you've caught the bug, then make sure that you keep a low profile. If you have a fever, don't come to school. When you do get back, check out the DVDs and watch those, and then try to keep a low energy level, because what apparently happens is if you start zooming along like usual, it'll come back at you again. So I'm recovering as well. Okay, today what we want to do is we want to go back to some very basic material, but we want to kind of look at it in a new approach. Yes, okay. We want to look at linear functions, which you have quite a bit of familiarity with, but what we want to do is start taking some real information, data that behaves in a linear pattern, and see how to model that data with this linear function modeling processes. So what we're going to do for the data modeling is we're going to learn how to use our technology, and you can do this by hand too, except by using the calculator, you're going to find it much more efficient to use the data saving characteristics or capabilities of the calculator, and then be able to generate something called a scatter diagram. So what we're going to do is we're going to store data, and then we're going to generate a scatter diagram. And then we're going to let the calculator use some statistical features to create what's called a regression line, or the line of best fit. Line of best fit. And the modeling we're doing today, as I said earlier, is we're going to take data that appears to be linear in its characteristics, and we're going to use our concept of slope and our slope-intercept type of an equation, which you're familiar with from beginning algebra, and then also this one, which is called what? What's the name of this? Point. There's a given point, isn't there? x1, y1, and a given slope, and so that's called the point-slope equation of the straight line. All right? So let's, this is in the beginning of chapter 3, so let's go ahead and grab something right out of chapter 3, and I think I'll throw it up here on the overhead and show us how to help you learn how to do that. First, look at this cluster of problems down here at the bottom of the page. This is taking you back to your beginning algebra background, these problems down here. Linear functions are given, and you'll notice it says determine the slope and y-intercept. Let's go ahead and kick up onto the overhead. There we go. And it says determine the slope and the y-intercept of the function, use the slope and intercept to graph the equation, determine the domain and range, and then determine the average rate of change, and is the linear function increasing, decreasing, or constant. So this takes you clear back to beginning algebra level with a little bit of college algebra vocabulary thrown in here. So let's grab one like number 18, has a little more something instead of a beginning level one, but maybe something like number 18 down here. Okay. So h of x is given to us as minus 2/3 x plus 4. It's very elementary, and you all should be comfortable with it. H of x is given as negative 2/3 x plus 4. Okay? Very clearly, the y-intercept is what? Y-intercept is the point 0, 4, right? Easy. The slope is -2/3. So with that information in mind, we could draw a sketch of this. We have to have a point to draw a linear function to get started, and then from that point, we then essentially stair-step our way in the defined criteria for slope, change in y over change in x. So we know that we would drop 2 and run over +3, and continue to do that, drop 2 and over 3. And so we get a series of points other than the 0, 4 location. Now what we could do is we could go back to the original equation and just find some other point instead of playing the stair-step game with our slope. Instead of doing the stair-step thing like you would in beginning algebra, we could just simply come back and take some other location besides x equals 0. So we could go to some place like, say, I would select an x that is divisible by 3, like 3 or maybe 12. How about if I pick 12? Oh, I like that. Okay, we'll be out there to the right of ways. Let's go ahead and put a 12 in. H of 12 is -2/3 of 12 plus 4. And so all you have to do is find another spot, because we know the function here is linear. So we know it's going to behave like a straight line, so all we need is a second point. We've got this point already locked in, and all we need is some other point. So I'm going to go way far away from that, clear out at 12, and I drop it in there, and I get negative, that becomes a 4 times 2 is -8. -8 and 4? -4. So we have a point, another point then out at 12 and down at -4. So we can go out here. It's going to be out here a ways. 12, -4, right out there. And then we're going to draw our line. Okay. Now, to answer those fundamental questions that were asked in the book, it asked a variety of questions. It said, well, why don't you tell me what it says, since I don't have the book right here in front of me. First thing it asked was,
determine the slope of Y-intercept.
Here's the slope.
Y-intercept.
Y-intercept, we did that.
Use the slope and Y-intercept to graph the linear function.
Did it. Including, notice, labeling a couple of key points to help us.
Determine the domain and the range of each function.
The domain, clearly.
-infinity to...
Everybody feel good? -infinity to the left, infinity to the right. See, I'm just making sure we're all up to speed on this stuff before we start doing some data modeling. And then the range. -infinity, as low as it can go, keeps rising up, off to the left in this case. Right? It asked that. And what else did it ask?
Determine the average rate of change for it.
Oh, average rate of change. Average rate of change. All that is, and I've mentioned this previously, is what? Huh? It's the slope. It's the slope. It's the change in y divided by the change in x. And in this particular problem, since the behavior is linear, the slope, the average rate of change is -2/3. So there's your average rate of change. Any other questions asked? Is that it?
Determine whether the linear function is increasing, decreasing, or constant.
Okay. Somebody else help me on this now. It's decreasing. Why is it decreasing?
Down to the right.
Because it falls to the right. falls to the right. So it's a decreasing function. Okay, so that covered all of the elements. All right? So let's now look at a set of data, or maybe we could find a problem, an application problem that, let's try to find something sort of real that's in the book, and then learn how to, let's come back right over here for just a second. Let's find something that's going to give us some data, learn how to store it in our calculator, or you could do it by hand by building a little table of the data, and then generate a scatter diagram either by hand or using your calculator, and then finally look at the data as graph and then generate a line of best fit. Once you have the line of best fit, you can then answer all of the kinds of questions that we're asking this basic problem here. Okay, so back to the book. Let's take one like number 28. Like number 28. So what I'm going to do is, just in the interest of completeness, since I'm going to be using the calculator here in a few minutes, what I'd like to do is go ahead and write this information up on the board. So we have a collection of data. -10, -5, 0, 5, and 10 on the x, and the y data associated with those points is 0, 1, 4, 9, and 16. Okay, so here's data. Looking at this data, is it linear? Is this data linear? What would have to be the requirement for it to be linear? For any change in x, in this case, plus 15 is a change in x, right? Isn't that what's going on between, oh, hold it. From -10 to -5? What's the change there? It's +5, isn't it? Okay. So for any change in x, and notice that it's uniform, isn't it? We have a uniform change in x from each data point, don't we? So our change in x is a +5. What's the associated change in y that you see over here? Change in y is +1 to here, +3, +5, +7. So is this data linear? Is there a constant change in, is this constant? Question? No, it's not, is it? It's not. What's the slope between these first two data points? I'm just adding more stuff to our table, notice. Between the first two data points, what's the slope? Help me. Speak up. Don't be shy. Change in y over change in x. Change in y is right here. Change in x. Help me. It's 1/5, isn't it? What's the change between the next two data points?
3/5.
Good. What's the change in the next? 5/5, which is? And between the last two data points?
7/5. So 1 and 2/5.
Okay.
So when they say it's staying constant, they're not talking about the range of y, like 1, 3, 5, 7, which it is a constant increase of 2. They're talking about it has to be the same as the x.
Well, this is the definition of slope, isn't it? Or average rate of change.
Right.
Average rate of change is defined as your slope that you're familiar with. Average rate of change. And what I'm pointing out to you from this set of data is that the average rate of change seems to not be constant. Okay, it's not constant. It's 1/5 between the first two data points, then it gets larger, 3/5 up to 1, and then 7/5, even greater than 1. Right? So is this data linear? No. So change in y over change in x constant? No. Okay, so the data is not linear. So what I'm doing is I'm showing you from a set of data how you can go back and discuss the issues related to slope or average rate of change just by looking at a data set. What are you more familiar with doing? Drawing a graph, aren't you? And looking at the graph. You're more familiar with looking at a graph of this stuff. So if I built a scatter diagram now by hand, a scatter diagram by hand, we can do that. And if I can do it here on a whiteboard with no grid, you can certainly do it on graph paper, okay? And so I can plot these data points. At -10, I'm at 0. At -5, I'm at 1. At 0, I'm at 4. At 5, notice I'm trying to, my scaling's a little screwy here. At 5, I'm up at 9. And finally, at 10, I'm at 16. Does that data look linear? Clearly, no, right? If somebody asked you, like if I asked you, how would you show me what these average rates of change are that we just discussed here on the graph, what would you draw? What would you draw on that picture? You would draw these slopes. Here's a slope. That slope happens to be what? Right there? 1/5. This slope, 3/5. The next one, slope of 1. Pretty good looking graph, huh? Okay. And then finally, a slope of 7/5 between those last two data points. Do you see how the average rate of change is increasing? Yeah. And so this function is growing, but it does not appear to be growing linearly, does it? Okay. Real world stuff does this. But you might take a trend like this and say, oh, I want the line of best fit, the straight line of best fit. So what we would do is we would look at this graph and we would probably, one way of doing it would be for us to take all of these values, and this would be kind of a pain, and average these together, average these slopes together. And what I'd be coming up with would be a slope, probably something like my hand here, right? If I averaged all these individual slopes. And then I would kind of look, where do I want to lay that line to get the line of best fit? Okay? So I just used my artistic talents to kind of eyeball where I would lay that line. Feeling good? Okay. So where would you suggest I lay it? Do you want me to just try it?
10, 16.
Actually hit that point?
Yeah.
I actually think if I've got these data values, maybe this is money. $16, $9, $4, $1, no dollars. Okay.
Okay, less.
So I'd probably come in a little lower than any one of those, or I'd be above some of the points and below some of the others, to make a long story short. So I'd probably just eyeball this with some line, maybe something like that. Okay? That'd be a rough guess. Now my sketch is not too bad, is it? I mean, considering I don't have any grid up here. So if I look at that thing, and I'm noticing that this point's here, down here at 4, that point's up at 9, it looks like my y-intercept might be somewhere, what, around 6 or so? 6? And what do you think that slope looks like, folks? Got a sense? 64 fifths? Oh, now that'd be huge.
About one.
64 fifths would be big. So it'd probably be something less than 7 fifths. Reminds me of the 3 bears, right? Too cold, too hot, just right. Okay. So too small, too large, somewhere between these. How about 4 fifths? Doesn't look like, let's see, 1 fifth, 3 fifths, 5 fifths, 7 fifths. Why don't we guess 4 fifths? And it's just guessing based on the picture. Okay? 4 fifths. So if I guess a y-intercept, this is a guess, and I guess a slope here of this, then my model, my data model would be, this is my guess, this is my model guess, would be y equals, what? 4 fifths x plus 6. Our model guess, just by rough sketching here, would be that for this data. Mm-hmm.
So when you're doing a line of best fit, you always start at the bottom, but not necessarily at the point that crosses the x-axis.
Yeah, notice I'm not hitting this point. Matter of fact, I'm not hitting any of the points with my guess there, right? I'm too low here on my guess. I'm too high here and too high here and too high there and too low there. Got the idea? You can take a ruler. If you've got your scatter diagram, you can take a ruler and kind of wiggle it and kind of feel where you think it should fit. And then you can simply look at that sketch you drew with your ruler and go ahead and write down what you think is a guess. Okay? And so the slope in decimal form would be 4 fifths is 0.8, isn't it? 0.8. Y equals 0.8x plus 6 as our guess. Okay, so this is the way you do it by hand. Matter of fact, back in the days when I was in school, a long time ago, we didn't have these fancy calculators, and we would do it this way. We would do it this way. And we would be able to do things like when I went through engineering school pretty darn accurately. Accurate enough to be able to do things like get satellites up into orbit and stuff like that on a much more sophisticated level. But we were able to do a lot of that stuff without using calculators. We use slide rules. Okay. So let's come over now and learn how to use the calculator to enter the set of data, enter a set of data, and then let the calculator generate the line of best fit for us. And before I do that, there is a handout. I want to make sure I get it up here on this viewing screen so that it'll be on the DVD. And this is the first part of the handout, and then I'll move that in a second. Back in the control room, does that look like that would be readable on a DVD? Okay, I need to bring it up a little bit. Okay, so I want to make sure this is going to be readable, so let me see if I can do this. Let let me back up just a touch. Shoot. How about that? Is that okay? All right, good. Okay, I want to make sure that people, and it doesn't quite catch all the writing there, but very close. Okay. To find the equation of best fit, these would be the calculator steps you would take with like a TI-83 or an 84 calculator. The actual commands on the calculator on other types of graphing calculators would be similar but somewhat different on different type of calculator. So what you're going to do is you're going to go to the y equals key. You're going to either turn off any equations, and I'll show you how to do that today, or you will disappear them, erase them. Then you'll go to your statistics set, and you will enter data into what are called data lists. And we'll be entering data into L1 and L2. And then there's a series of commands here, and what I'll do is I'll walk you through this. But if this is readable on the DVD, then somebody could pause the DVD and write these things down. Let me just go ahead and for completeness and move down here so that the second set step would be shown. Here it is, step 2. And we'll go over this in a minute. And what I want to just point out to you in the second step is over here on the right, here's linear regression right here, and we're going to be doing that today. But notice, and tomorrow or the next class session, we'll be doing some of these others. So there's all these different options available for generating lines of best fit or curves of best fit. This is that series of commands. And then finally, step 3 is to then take graphing your scatter plot and then being able to get that curve or line of best fit to actually lay on top of your scatter plot. So these are the commands for that. Move that over a touch. Okay, and I passed this out to everybody. So everybody should have a copy of this handout. Yes, they're up here. Okay, so now using the graphing calculator, and I will back up a tad here. I think that actually is pretty good. Here we go. Okay, I'm going to go ahead just for interest's sake and follow the steps that are on that sheet I just showed you. So what we do is we turn our calculator on. We go to y equals, and let's say that I did not want to erase this particular function, but the instruction said turn this thing off. The way you can turn off a function without erasing it is you can move over onto the equal key and hit enter. Notice the cursor, notice the black darkened equal sign. If I hit enter, the equal sign looks differently now. See? So that function's still there, but it's turned off. It's turned off. All right? Next step. It says go to the stat set. Now, I just hit the stat key, which is right near our blue arrow keys. What the command said to do is to go into edit. Now what I want to do is I want to show you something. When I go to edit, there's probably some data there from some work I've done previously. And when you play with these things, same kind of thing will happen. There's probably some data. Notice I have a bunch of data there. Okay? Let me show you how to clear a data set first. So go back to stat, and then notice item number 4, clear list. So I go to item 4, and now on my keys numbered 1 through 6, I see on the case of the calculator L1 through L6 on the numbers 1 through 6. So what I can do is I noticed I had data in L1, 2, and 3. So I can go shift or second L1, comma key is above the set number 7 key, and then L2, comma, and then L3. Okay, so I can specify a series of several lists at one time, and if I hit enter now, it tells me I'm done. Now I go back to stat, select item 1 for edit, and notice the lists are empty. Now, it's real easy, and you'll be real fast at this real soon with a little bit of practice. We can now enter the data into our L1 list. So we're going to go -10, -5, 0, 5, 10. I think those were the numbers in our problem, weren't they? And then I arrow to the right. Now I need to make sure that I put in exactly the same number of items in both lists. Everybody hear that? I need to make sure I put the exact same number of items in each list. Otherwise, if I try to do something with this, it'll give me what's called a dimension mismatch. If you ever see that error message, DIM mismatch, that means that you have data that's not equal in number in each set. So this set of data was 0, 1, 4, 9, 16. 0, 1, 4, 9, 16. Everything's good. Data is in the memory of the calculator now. Quit. Let me show you something. If you want to check this back on this home screen, I just hit quit.
How did you quit? Oh, there it is.
It's shifted on the mode key right there near the top of your calculator. So I got back to the home screen. And if I want to see what's in the L1 list, all I have to do is go Shift L1, and here's that set of data. I could go Shift L2, and here's that other set of data. So I could spot check to make sure I entered my data correctly. Okay. Next step, we'll just follow what they told us to do, is we now go stat plot. Now stat plot is on your Y equals key. So we go Shift stat plot on your Y equals key. And now what we want to do is we want to turn one of these on. The calculator has a capability of plotting 3 statistics plots at the same time. So we're going to go to item number 1 just to turn this guy on. We hit enter, which now activates plot 1. And we step down, and this is a scatter plot, this first one, and that's the one we'll want. What this one would do is it will take the data points on your scatter diagram like we drew by hand, and it will connect the data points with straight lines, similar to what I did on the board. This is kind of a bar graph, sort of a frequency diagram, and then these things are called bar and whisker. Something, I think that's what they're called in statistics. Then we have, I'm going to go ahead and hit enter right there. And notice now the default settings down here, I could choose, I could use the L1 to L6 to pair up my data for my X data set and my Y data set. So if I had my X data maybe in L3 and my Y data in L5, I could set it up by just choosing those commands there. But it's already, the default setting is this. And then down here, so these are all good. Everything's looking good. And I hit enter here for my scatter diagram. And then down here, this is going to leave little square boxes, little plus signs, or just a pixel dot. The pixel dot's not very good. It's so tiny. I usually use the box. So this is all set. So I now quit. And so if I go to Y equals, notice something on the Y equals screen. This polynomial function is turned off. As I mentioned earlier, it's off. But notice up top. Now you're going to have issues with your calculator on this kind of thing, and I answer this question all the time with people. They come in, my calculator isn't drawing my picture, and they're doing some kind of function thing. But what happened somehow is they got up here, and that thing's dark. And they're really not doing a scatter diagram at all. Okay? So if you see one of those darkened, that means they're turned on. Okay. So we have stat plot turned on. Now what would be the next thing for graphing that you normally would do? Viewing window, right? Your left and your right and your bottom and your top. So we know what our data looks like. And so what I would do now is go to my window and set up an intelligent window. So I know my data was over at -10. So I'm going to go -15 just for the fun of it. And how far to the right did we go? +10? So let's go to 15 there. And why don't we put tick marks every 5? And vertically, our Y data, it went down as low as, how low was our Y data? 0. So I'm going to go down below that a ways. Why don't I say -5, and let's go up as high as 20 and put tick marks every 5. So I just want to make sure that I'm lower than the data and higher than the data. And now I'm going to hit graph. You're going to love this. This is much better than doing it by hand. Boom. Isn't that neat? If you turn trace on now, turn trace on, and look at what it labels. Up here at the top, it tells you that you're doing a stat plot. It's called labeled P1, and the data set is L1 and L2 being used. Really cool. And down here, look at this. It puts you right on your first data point in your set, down here on the bottom. Okay? And so we can move our arrow, we can take our right arrow key, and look at the way it jumps from one data point to the next. And nowhere in between. Right? Nowhere in between. It only allows us on a scatter diagram to be right on that data. Okay, here's where the fun part comes. I could come back here now, and I'm going to clear this polynomial out of here, and I'm going to put my guess, or our guess, in there.
Now, did that really go away this time?
I erased it.
Okay.
I just hit the clear key to get rid of that Y1 thing.
Because you had it off, could you have left it on there and just
Sure.
done it on Y2?
Yeah, sure. Could have. So what I want to do here is I want to take my mental guess, my rough sketch on that whiteboard. I guess the slope was 0.8, right? 0.8x, or 4/5 times x, plus eyeballed it at a 6, didn't I? And if I go graph, it comes in there pretty much like that line I drew on the board. Okay? However, what's going to be asked in your book and on test and in MathXL is, what's the equation for the line of best fit? They want the calculator to do some adjusting, folks, and to minimize the differences between these values, between what the guess line is going to be, and so it wants to get something probably more accurate than me just eyeballing it. All right? So let's let the calculator do it, and what I'm going to do is I'm going to leave this one in the memory. I'm going to leave that sitting right there because I'm curious to see how good we are with this guess. So here's how we do it. Quit, come back on your home screen. Ready, back on the home screen? Okay. Let's let the calculator generate a linear regression equation for us. So here's how we do it. We go back to stat now, and look at this menu set. Right here doesn't look like it's too good. This means sort data in ascending order, assort it in descending order, clearing the list we talk about, and don't worry about that last one. But look across the top. This looks like it might be a good spot to go to. Calculate. So I arrow to the right, and it brings up, oh, this is kind of neat. We're doing kind of two variable statistics, but look at this, linear regression. What's the slope in this equation right here? What's the slope, folks? Letter A, letter A. What's the Y-intercept? Letter B. What do you think this means? Where the pencil's pointing. Quadratic regression. Generate a quadratic function. Now, actually, that data probably would be better doing a quadratic model, wouldn't it? The way we looked at, I mean, we saw the sketch kind of curving like a parabola. So that'd probably be a little better one. Cubic. This is not like a quart of milk, folks. This means quartic. This means fourth degree polynomial. And I want to show you something. Let's go down here further. See that arrow on the number 7 there? That means there's more stuff down below. Oh, here's another linear regression model. What's the slope on this one?
B.
B. What's the y-intercept? A. Okay? See? It. The thing that's multiplied times x is your slope. Okay. Keep on going. This is natural log regression. Later in the course, we'll see these things. Exponential regression. Power regression.
Does regression just mean make us an equation?
Yeah, just think of it at this point, until you take a statistics course, think of it as your line of best fit, or your curve of best fit. So there's all these different ones built into the memory of the calculator, and then it uses statistical methods to generate the best one for you. So we're going to go back up to the top and come down here and select item number 4. So I hit that, and then I specify the 2 lists we want. It will understand L1 and L2 if I don't do anything right now. It'll understand if I hit enter, it'll treat L1 as X, L2 as Y. If you're using any other list, you want to put the names of the list with a comma separating them there. In other words, example, L1, comma, L2. Now I hit enter, and it does all the work for us. Watch. Oh, that's exciting. Wow.
So we were right.
Man. I did not.
Because you know everything.
I did not do this. I did not do this problem ahead of time. Okay?
You're just that good.
Yeah, I've just been doing this for so long, I guess. Okay. So anyway, it happened to nail it. I didn't expect that to be the case. Okay, now, what we would want to be able to do is we want to be able to take this equation without having, this is simple. I didn't expect this at all. Okay? So normally what you would do is you would normally want to write this down on your paper. Y equals 0.8x plus 6, right? As your regression model. So what you then do, normally these numbers are not going to be near this nice. So to get the calculator to actually store it for you, you come to an empty spot, like Y2 or any of these others down here, empty spot, and watch this. Let's see if this is, yes, it is on that handout that I gave you. What you do is you come to an empty spot, and you want the calculator to automatically stuff the regression equation into this Y2 location, automatically. And the way you do it is you go to variables key, which is over near your blue arrows. You hit variables, and VARS, V-A-R-S is the abbreviation on the key. And then item number 5 down here is statistics. And there's some weird looking symbols here. I'll tell you what a couple of these items are. This is the number of items in your list. This is the average value of those items in X. This is the sum of the X values. This is what's called the standard deviation on the X values. This is the average value of the Y's. This is the sum of the Y's, the standard deviation on the Y's. So someday, some of you may have already taken a statistics class, so that's the reason I mentioned those. What we want to do is go over here to equation. Ah, there it is, hiding in this menu right here. There's our regression equation. And so what we do, we were in Y equals, remember? Everybody remember, we were in the Y equals in an empty spot, and what I do is I get to this location and I hit number 1, and boom, it stuffs it in there for us. It stuffs it in there for us. All right? And I hit graph, and this is boring because it fit exactly what my guess was earlier, right? Okay, and it lays it right on there. Now when you turn trace on, folks, you can now arrow down with your blue arrow key, and it jumps onto your other functions. Here was our guess function, y1. If I go to y2, there's my regression equation. When I'm on y2 in the trace mode, I can now move across that in between the data points. Here's some vocabulary. How many of you will be taking chemistry? A bunch of you. How many will be taking some business classes? Another bunch of you, okay? So you're going to hear this kind of vocabulary frequently in these different areas of science, business, and so forth. And so what we can do is go between data points, folks. We can go between data points, and that's called interpolation. Interpolation, going in between data points, interpolating. We used to have to do that by hand. Now we've got these fancy calculators that'll do it for us. So if I said I was at 2.5 with this line of best fit, my guess on the y value would be 8 if I was at 2.5. What if I was outside the data set, say up over here at maybe around 13? 13. I would be extrapolating. I would be going outside the data set to the right, outside the domain of the data set, and I'm extrapolating using that linear model. A guess of the behavior at 13 is 16.4. Okay? Interpolating goes between data points. Extrapolating is outside data points. Okay. What if, let me clear those two functions out and keep my data set. Watch this. I want to show you something else really neat with the calculator. Let's say I want to alter that data set. I only want to alter one data point. Two ways of doing it. I could go to stat. I could go into edit and come down there and change one of the numbers. I want to show you another way to do this. Let's say instead of being a value of 9 when I'm at 5, I want to be in L2, I want that value to be 12. I want that value to be 12. Okay? In L2. Okay? So that's element number 4 in L2, isn't it? Okay. Let's see if the calculator understands this. I want that value to be 12. And I want to use the store key, which is down next to your on key, just above your on key, store. And then what I'm going to do is I'm going to now punch L2 in parentheses. I want that to be element number 4. Now, if I graph, there's that 12, folks, in the data set. And if I ran the regression thing real quickly, item number 4. There's the equation. Look at the way the slope changed, and the y-intercept changed. See that? Okay. So you can make adjustments to the data. You can come up with a new regression equation pretty easily. Okay. I think that wraps things up for today. Linear behavior. Next session, we'll start playing with quadratic behavior, and that'll be tomorrow, right here.